when you look at it, is that it is longer. Instead of 15 lines of code, it is now 20 lines of code. And this is kind of one of the sad results of any kind of countermeasure you add. It makes the code longer and more difficult to debug and more difficult to maintain, and it takes longer to run, and so on. So this isn't so good. And now let's see what's going on in this function. Can anybody, who else cannot see? Anybody not seeing the picture? Okay. Sorry, Ali. I hope you'll get better. I'm sorry. So okay. So let's see what I'm doing here. First of all, I'm not returning in the middle of the function, only in the end. So I have a variable result, and I'm going to reset the value of result in the middle and return in the end. And another thing I'm doing is I'm not going to exit if it's the wrong length. I'm going to add some padding. This is between lines 7 and 11. This is some kind of JavaScript thing which pads the input and the password so they're the same length. And let's assume that this is the maximum possible length of the input. So now I know that after I get to line 11, in password and secret password are the same length. And then I am only setting the result to false and returning. The purpose of line 11, it's not really necessary. I'm padding it to the same length. Indeed, I could have just padded it when I saved it. It's certainly possible. Okay, so can anybody find any problem with my secure function? Okay, line 15. In line 15, I set results to false. Okay, so what is wrong with that already? Okay. Okay, so my execution time still depends on the data. And in fact, I have to tell you that this function is actually less secure than the previous one. And why is that? How many times do I run line 15? No, I don't run in the password length. I run line 14, the password length. Indeed, as it all says, I run line 15 once for every incorrect character I have. So now, what can I do as an attacker with this data? I can still measure the time. This is my session. I measure how long it takes. But does it help me that line 15 runs as many times as there are incorrect characters in the past? Yes. So I now know how many errors I have, and then I can play a nice little game called Mastermind. Do you know Mastermind? Bulpgia? You know the game? I don't need to do trial and error. I can actually, if I play it right, this can actually be done in constant time. If I play the combinatorics game right, I can have a constant amount of queries and get the password. So this is actually much more insecure than the previous one. So what can I do to this function to make it secure? I'm kind of disappointed. What can I add here to make it better? Okay, so Shachar is suggesting. I don't want you to tell me again how. Okay. What did Dima say? Hangman, yeah. Bulpgia is. So Shachar is saying that in line, which line would I add that? In line 16, Shachar? So if I add else result equal to true, then that I will only be checking the last character. So it will be overwriting the false with true, and I will only be checking one character. That's even worse. So Shachar is saying, instead of else result is equal to true, I'm trying to do what Gil is saying, else result is equal to result. So result is equal to false, or result is equal to result. So I have one function running instead of the other. Let me tell you something about that, because you are, again, this will probably not work. And why will result equal to result not work? Because in assembly language, result equal to true is set variable to constant, and result equal to result is either set variable to variable, or the compiler is an optimizing compiler and say, you're not actually doing anything. I'm going to eliminate this function. You're not going to do anything. Result equal to result is going to be eliminated. Do not trust your compiler. That is a very good rule for life. What about JavaScript? JavaScript has a compiler. The compiler just runs in a different time. In C, it runs before you run. In JavaScript, it runs just in time, but there is still a compiler. OK, so Alina is saying result is equal to pointer. Oh, result is and. Logical. OK, so I'm ANDing the result with the password. So again, my compiler is going to be clever about it and saying, first of all, I'm going to do the comparison, and then I'm going to do the AND. But the AND is with 0, so it's AND with 1 is it's not. The compiler is going to be very, very tricky about optimizing. So does anybody have a suggestion for something I can put in the else? With the hash, you will have to wait a moment with the hash. What can I put? Result equal to false, else. I can't do result equal to true. I can't do result equal to result. What can I do? Anybody have a suggestion? Oh, indeed. OK, so Gil is suggesting result 2 is equal to false, or temp is equal to false, or shekel. OK, this is a very nice idea. It's called prophylactic write. Prophylactic write. I'm spelling it out. Prophylactic write is the idea that you want to write to a garbage value. So you're going to do the exact same machine code instruction. You're going to write constant to variable to register. It's going to take the exact amount of same time. And then Gil is saying, OK, and the compiler is going to see that nobody is looking at result 2, and it's going to throw away this entire branch of code. So that's a problem. But we can volatile, or we can result to. No, again, you're moving a variable to a variable, not a constant to a variable. It's going to take a different amount of time. And if you make it true, then the compiler is going to. So what you can do in the end, after you can do return result and temp, indeed, what Owen is saying, which will work for not optimizing away temp. But there is, again, a problem, a very tricky problem with this. And this is called, does anybody know what it is? Does anybody here know what branch prediction is? Branch prediction. Branch prediction is one of the tricks that a CPU has to run really quickly. We're going to go a little more into hopefully into Spectre and speculative execution later in the course. But I just want to tell you that the CPU, not even the compiler, the CPU is always trying to guess what is the next function which is going to run. And if the compiler is guessing right, the CPU runs faster. If the compiler is guessing wrong, then it says, no problem, these are transient executions. I'm going to retire them. I'm going to roll back the state and keep on running from the right state. And it's going to be explained in more detail when we go into Spectre. But what happens is that when the first time you have result 2 is equal to false, the CPU is going to be very, very surprised, and it's going to take the CPU longer to run, because it's always thinking that result is equal to false, because usually the password is incorrect. So eliminating the if is you're just coding it so it looks like there's no if. There will be an if. Okay, so there is a problem with this countermeasure, but again, you can say, okay, I'm using a compiler, I'm using this really cheap microcontroller that doesn't have speculative execution, or I'm using a straight assembler and I don't allow any compiler optimization and so on. So it's possible to write secure password checkers. I'm just saying it's not. You have to be very, very careful about it. So now I want to show you the next implementation I have, and this is the one that everybody here was clamoring for, and this is the hash function. So what do I do here? I'm going to take the inputs. I'm going to hash it. So a hash function, I think you all know what hash function is, but just to make sure we all remember, a hash function receives any sort of input, doesn't really matter what input it gets, and the output is always the same length. And this is nice about hash functions. But what is also nice about cryptographic hash functions is that if you're really two values which are really, really close to each other, their hash values are really, really far away from each other. So if one bit is different between two values, then by the avalanche property, how many bits of the hashes are different? Not two. Half, indeed. Oh, yeah, that's right. Half of the bits are different between, about half, not exactly half, but about half. It's not all of the bits, it's half of the bits. So because these different gets mixed really, really well. So one moment, Lido, I'll go into this, but if I'm using a hash, then the hash, the line 11, I won't be able to get any good information out of how many times line 11 is running. If it's running 1 time, or 2 times, or 3 times, doesn't matter, because the hash doesn't get closer when I get closer, when the pre-images get closer. And so there's one small leak in this function. Does anybody see it? Tiny, tiny leak. Yes, indeed. In line 7, I'm leaking the length of my password. How can I get around this? But then I'll be hashing a different value. Yes, so what is right. I don't need to do hashing of the secret password in secure context. I can do it outside. In fact, many Unix implementations don't store the password at all. They just store the hash of the password because there's nothing to do with the password. If the only thing you want to do is to compare two values, you can compare their hashes. It will be as effective. So if I hash the secret password and save, instead of saving the secret password, I just save the hash, then this is as secure as possible, because there's actually no secret information being processed in this verified password, and there is no secret dependent data in the timing. So in fact, this is a good prevention countermeasure. Password checking is a very specific case for which there is a good solution. Okay, so now after we saw a couple of countermeasures, just as a little interlude, I want to go again to the cypherpunks mailing list and show you a response written by, oh, I think I need to do this twice. Where there was a big discussion thread after Kocho posted his attack. And what is the nice here is saying, timing attack is a pretty obscure attack, and one which most implementations won't ever need to worry about. because it's much easier to get the victim to download some applet that patches the browser. So what they're saying is timing attacks are very exotic and a nice thought, but there are lots of other ways of getting to the user secret. And again, we're seeing this kind of discussion between the typical vendor response, between the attacker and the system engineer, which says, you know what, it's not this code. Yeah, and you can look at the you can look at the cypherpunks mailing list. It's fascinating to see how much similar is their response to the responses of vendors today, even though this has been going on for quite a long time. Okay, so now I want to talk to you about your homework assignment, which is